FT state. I'll try and okay. So let me just try and before I start this talk, let me just briefly mention that this is work that's based on largely work with Kyriakos. So we've written many papers on this. I won't summarize. I'll try and take some particular path through it. And also based on work with postdocs with Kyriakos, Shawik, postdoc with me at ICTS, Prashant and Sudeep, who's a student at ICTS. I wanted to try and make this talk as sharp as possible. So rather than talking about paradoxes and so on, I'll try and turn this into a constructive question. And so I'll try and focus it and try and make this as sharp as possible. And so the question I want to ask in this talk is whether we can use the CFT to give a description of local bulk physics in AdS. So that's a well-defined question, and one can ask if it has an answer. And so I try not to talk about firewalls and so on till absolutely the end. And this is a question which all of us who are interested in AdS CFT should be interested in. Okay. So usually, we formulate AdS CFT as a relation between the boundary values of bulk correlators and boundary correlators. So we say that here's some bulk correlation function you can compute in the bulk theory. You take its limit as z goes to 0 in this coordinate system. The boundary is z goes to 0. You strip off some leading paths that are dying off. So you have to enhance the correlator as it goes towards the boundary. And this boundary value of the correlator is the same as a certain correlation function computed in the boundary. And the AdS CFT dictionary tells us for every field in the bulk file, we have some other operator on the boundary, and this is how AdS CFT is usually formulated. So the question I want to ask, which is a natural question, is whether rather than just talking about the boundary values of these correlators, if you can directly try and describe these correlators at some point in the bulk, where z is not necessarily 0. So can you try and come up with some description that answers what this is in terms of some correlation functions on the boundary, and more ambitiously, and in some sense, this is the way I'd like to formulate it. Can you try and describe the bulk operator, the field operator in the bulk, given at some point in the bulk, x is some transverse coordinate and z is some radial coordinate in terms of CFT operators. So this is the question that I want to ask, which is slightly different from the usual way in which AdS CFT is formulated. Now sometimes people object to this because this is not quite a gauge invariant question. You don't have gauge invariant local operators in gravity. And so, you might say the only thing you can really define in a theory of gravity are S matrices, and these are not good gauge invariant questions, so why do you even ask it? In fact, in AdS, the situation is slightly better. And the reason the situation is slightly better in AdS is because you can use the boundary to define at least quasi-local gauge invariant observables. And the way you do it is you start from some point in the boundary, say this point, and then you jump in. Okay, say you jump in along a light trail, along some geodesic, and you have to normalize your affine parameter in some way, which you can do by bouncing light rays back to the boundary. And so you jump in from the boundary, and you wait a certain proper time, or you wait a certain affine parameter, and then you ask what is the field at the point that you reach after doing that. So as you can see, this is not quite a local observable, because it's related to the boundary. It's a relational observable defined with relation to the boundary, but it's a little bit like having some Wilson and Eichler stretches all the way out to the boundary. And this is a good, observable to speak about in AdS CFT. It's not
in which direction.
So good. So you have to define, for example, good. So this is all the things you can make precise. You can say you jump in radially inwards, for example. So you can make
so the parameter set of such things.
Set a parameter set of such things. That's right. So you can use this to mimic the bulk parameter coordinate. So basically, what you need to do is replace the bulk radial coordinate with some affine parameter or some property. So these are things you can make precise classically. So at least classically, this is I can try to describe this to you in more detail. It's not very hard to do.
So why don't you do the same thing in flat space?
In flat space, the thing is that, so this is not something that's invariant under all diffeomorphisms. It's not invariant under large diffeomorphisms that change the boundary. So in flat space now you have to, you have to decide where you jump in from.
Primates.
Well, okay, so then you have, then you have to wait, okay, so you have to wait an infinite amount of process. Okay, so maybe you can also do it in flat space, but in AdS, all those complications also don't apply. Do it in finite amount of proper time. You don't have to worry about, what kind of subtraction procedure you're using. Here was infinity, here was the cutoff, and how do things depend on the cutoff. So those subtleties are also not there. Maybe you can do the same thing in flat space. But I'm just saying in AdS, you don't have to worry about even those subtleties. Okay, good. So this is it's a well-defined question. Maybe you can do the same thing in flat space as well. But here you don't have these issues about, even having to cut off the space. You can just jump in finite time. Okay. So now,
Suvrat, so these observables which you have in mind, I
yes.
mean, can they be sort of quantifiably written in terms of some chemical line or something?
Yeah, I think it's so classically this observable that we are right now here is very similar to just setting up some coordinate system in AdS and writing down a field at that point. So I mean this is it's not quite a Wilson line, but really the statement is how do you define when I talk about Pxz, how do I define what my coordinate system is? Now how do you pick a gauge? How do you pick? And this is the way of picking a gauge. Now you can pick a gauge, of course, by choosing some Fefferman-Graham gauge or something like that. There are other ways you can pick a gauge, but it's just a nice way of picking a gauge. It's just picking a coordinate system in the bulk. So it's a particular way of setting the coordinate system in the bulk. I mean, this is all that this is doing. And there are many other ways of doing this. Numerical people, for example, use this harmonic gauges. So you can set up gauges in many ways. This is just a particular way of deciding. Saying when I say Pxz, this is what I do.
When you say jump along line, it doesn't matter to you, but you're doing it along line.
I'm doing it along line trace.
So congruence, nothing going to.
Yes.
So is it in AdS or in any deformed AdS that can dynamically rise when you?
Yeah, you can do this in deformed AdS for sure. Yes. So this
But
is a particular time.
then the question is which direction you jump in would be more complicated.
So the thing is,
In AdS it's certainly well defined and you can probably.
right, but the asymptotic conditions are always fixed. You see, the issue of what direction you jump in is something that's fixed from the asymptotic directions. Okay. So just to make this precise, what you want to do is you want to jump in and send some light rays. Okay. If the asymptotics are fixed, you don't have to worry about what direction.
Convention.
So you choose some convention near the boundary, and then you're set. What you're worried about is what's happening in the bulk.
Well, in a general space, even asymptotically AdS, you wouldn't be able to choose some canonical coordinate system, which is what you're doing.
So you can use a
And there is no
coordinate system on the boundary,
Sure.
and then you can use that to fix something in the bulk. I mean, this is not a canonical coordinate system; it's a choice of a coordinate system, which is gauge and weight. You can choose some other coordinate system. Okay, am I answering your question?
No, but in AdS it will certainly work. How it would work in a general space that is asymptotical AdS, I do not see, but maybe you can see.
Sorry, but I don't understand. The issue is just so this is a space which actually has a let's say this has a black hole. So this is a space which is asymptotically AdS. What you're saying is you jump in from the boundary, you send a light ray, you wait for some proper time, and you reach a certain point, and that you ask what is the field at that point, and that's a well-defined classical question. Independent of what
Black
space.
hole destroy all symmetries. In the interior, destroy all symmetries.
But you're not interested in what the symmetries in the interior. What you're asking is a question of, I send a light ray from here, from AdS, what point does the light ray reach after a certain affine parameter? Whatever point the light ray reaches, tell me what the metric at that point is. You're not interested in whether the interior has any symmetries or not. So, I'm not trying to set up the relation between the usual coordinate system that you set up and this coordinate system may be different depending on the bulk excitations. So you might, if you set up two different coordinate systems or chose gauge in some other way, the translation between these two would depend on what's happening in the bulk. But this, as per se, is a perfectly well-defined coordinate system. Okay, we can talk later if you like. Okay, so let me try and give you the answer in empty AdS. The answer in empty AdS is actually well known, and it goes as follows. Basically you take these boundary single trace operators that you have, you Fourier transform them, and you multiply them with certain mode functions. I'll describe these mode functions in a little more detail just in a couple of slides later. And this gives you a certain operator. This is still an operator in the CFT, because what I did was I took the boundary single trace operators, I Fourier transformed them, I multiplied them with some functions. These functions are parameterized with some coordinates, and this still gives you an operator in the CFT. And you can write this transformation, which I did in two steps, by first writing down the Fourier modes of the boundary field and multiplying them with some other space-time modes in a single step. And so this tells you that the relation between this operator, which is a CFT operator, and the single trace operator in the CFT goes in this way. Okay, so you write down the single trace operator in the CFT, and you integrate it with some kernel. You integrate it all over the boundary. You get some other non-local CFT operator, and this kernel is sometimes called the transfer function. And it's been studied a lot. It was, by Benna and Hamilton, Cabart, Lifshitz-Low, and many other people. So this properties of this transfer function have been studied a lot. And so you can use this to write down a non-local operator in the CFT. And the claim is that these bulk correlators, the question that I asked in the beginning, how do you describe bulk correlators, are just described by taking CFT correlators of this kind of an object. So you take, You write down just CFT correlators of this known local object that I wrote down, and that gives you what bulk correlators are. And in fact, even more precisely, the CFT operator that is obtained by this transfer function method is dual to the bulk local field. So this is the answer to the question in TDS, and this is something that's been understood for some time. Okay.
But Z in the CFT then?
So Z is just a parameter in the CFT. You see, this is the only CFT operator. And now Z is just a parameter in the CFT. I multiplied with some mode functions. The mode functions happen to depend on T, omega, and Z. And Z is just a parameter. So you have to choose this mode function correctly to be a function of Z, so that you get the right correlators.
I think in the middle equation, this Z should not be there on the left hand side, isn't it? I mean,
sorry. This should not be there. This is just omega m. I apologize. So it's not omega of T omega Z. Sorry. This is just omega m is OT of omega is this bracket should not be there.
In that slide, where is the bulk field?
So the claim is that you wrote down some CFT operator,
yes,
and the correlators of the CFT operator answer the question I asked in the beginning, which is what are bulk correlators in the CFT? The claim is these are the answers to bulk correlators in the CFT.
How are phi and phi CFT related?
So this is phi CFT is a CFT operator. I'm claiming that this CFT operator is dual to the bulk local field.
Which bulk?
There's an AdS CFT duality in which there's some bulk local field, so you quantize gravity. There's a bulk local field which you can define by quantizing the theory of gravity and asking what is the field at this relationally defined coordinate.
Yeah.
What is the CFT operator that's dual to this bulk operator? It's this operator.
Sorry, where did the information of phi come in the integral for phi CFT?
Put in where is the information? And the claim is I'm writing down the CFT operator and I'm saying this is an addition to the AdS CFT dictionary that says that phi in the bulk, the operator phi in the bulk is. So if AdS CFT is a duality, then you believe for every operator you have in the bulk, there's an operator in the boundary. Okay? So you have this operator in the bulk theory, which is phi at this value of T omega Z. What is the operator that's dual to it in the boundary theory? This is the operator that's dual to it in the boundary theory. So phi CFT is defined as I described previously. So that's the question I'm trying to ask. What is the dual to bulk local operators? The local was defined using this relational gauge in the CFT. Yeah.
The choice of Z would decide what gauge the gauge you are using is
the mode functions would control it. That's right. So that will be important in later. Okay. Good. So now let me try and answer this question about a black hole. This answer is a little less well understood.
What properties do these bulk local operators?
Good. Let me say a little more about these properties. I'll say a lot more about these properties. In particular, one of the properties that you want is that that you want for things to be consistent is they should give you the same correlators, these boundary, that you would get by quantizing fields about curved space-time, about AdS. So these phi CFT correlators, whatever they are, by computing them, you should get the same correlators that you'd get by quantizing quantum fields about curved space-time. That's, for example, one of the properties that you want. I'm going to say more about what properties I want these things to satisfy. Okay, so let me try and say, what do you want, how do you do this in black holes? So what you do in black holes is, you again look for mode functions that satisfy. I'm specifying now the mode function a little more precisely that I wrote. So you look for solutions to say, the box theta equal to 0, and then you normalize these solutions so that as r star goes to minus infinity, which is where the horizon is. These solutions look like a sum of plane waves. Okay? So these are solutions that are normalizable at the boundary. Okay? They're normalizable solutions at the boundary, and at the horizon they look like a sum of plane waves, but this delta is something that you can compute. And there's of course some spherical harmonic thing. And then you take the boundary CFT and you compute this commutative. So you look at O omega dagger, you look at trace of e to the minus beta h, you just know from time translational invariance in the boundary, this has to be proportional to delta of omega minus omega prime, some delta of mm prime, and then there's some function that you get that depends on beta, this omega and n. It's some function that you can get, which given a CFT you could compute, and you set this e of omega n to be O divided by this root of c. And then the claim is that this phi CFT operator is just defined by taking this A operator, okay, defined as the Fourier transform, the single trace operator divided by square root of the commutative, which is here, and multiplying it with these mode functions. And of course, adding the Hermitian continuum.
Sorry, Suvrat, you are solving this theta in the gravity side.
Yes. So the claim is that this is just a function right now. Just a function of T, R star, and omega. So you take this bound, this is the operator, take this boundary operator, multiply it with this function, sum over all of them, it gives you another operator on the boundary. And the claim is that this operator is what is dual to the local bulk coefficient. And one of the immediate consistency checks you can do is, you can check the correlation functions of this operator taken inside the thermal trace, reproduce correlation functions of a field quantized about a black hole background. Okay, so that's actually the central property that you want to discuss.
And Suvrat, your mode functions don't show any absorption, is it? I mean,
no. So you have to look at normalizable modes. When you quantize fields about a black hole background, you impose regularity at the horizon, but you don't, and you impose normalizability at the boundary, and then you get normalizable modes. Now, the way quasi-normal modes appear on this is if you take some 2-point function, you wait for some time, you can approximate this by looking at poles in this normal Green's function in terms of the sum of quasi-normal modes. But you don't quantize a field in terms of quasi-normal modes. You can only quantize a field in terms of normal modes. It might still be the case that the response function can be approximated as a sum of quasi-normal modes.
So omega has no quantization.
No, omega has no quantization. About black hole, omega has no quantization, flat space omega.
And also delta is always real. I mean, e to the power I delta is a pure phase.
E to the I delta is a pure phase. Okay. So now, as I said, the main central property you want is that you want, that these correlators should be correlators of fields quantized about a black hole background. But there are other non-trivial things that come about it. For example, you can check that.
Sorry, since the last talk it's probably going to be important, I somehow didn't intuitively get this stuff.
Why this is the correct answer?
Yeah.
Let me say a little more, maybe it'll help you understand why it's the correct answer.
Okay.
So, one reason it's the correct answer is that, it tells you that. So the reason actually, let me explain. You see, what you want is E omega into A omega dagger should be 1. That is ensured by dividing by the square root of this commutator. So there's some commutator, but now with this, E omega into A omega dagger is 1. Okay. Now I've normalized it so that near the horizon, these things go like plane waves. So if I impose canonical commutation relations near the horizon, you see this is the correct quantization. This doesn't guarantee it's the correct quantization near the boundary, but it is the correct quantization near the boundary. So you can see that if there had to be an answer, this is the only correct answer. You look at the place where it looks like plane waves, you multiply it by canonically quantized annihilation trace operators, and then AdS CFT tells you it has to behave correctly near the boundaries, right? Okay. So now the claim is that, okay, so you can see already that there are non-trivial aspects. For example, there's something called the KMS condition that tells you how the 2-point function of these guys is related to its commutator. In this case, the commutator is just 1. And so you can check that just based on general considerations, the trace of e to the minus beta into this 2-point function gives you its Boltzmann fact. Because 1 by 1 minus e to the minus beta omega. And this is just as a result of some general properties of thermal states in a CFT. But this has a natural bulk interpretation. The bulk interpretation is that this is the thermal occupancy of Schwarzschild modes in the Hartle-Hawking vacuum, about a free black hole radius. So this is related to that. Secondly, and something that will actually be important for what I'll say, is that I said everything so far in a thermal trace, but we expect the boundary CFT, and this will actually be an assumption in what I'll say. You can see if you get rid of this point, then in fact a lot of the problems I talk about will go away. But we believe that the boundary CFT satisfies the axioms of ordinary statistical mechanics. One of them is the so-called eigenstate thermalization hypothesis, which tells you that if you take some generic state in the CFT, a generic pure state in the CFT, then correlation functions in this generic pure highly excited state look like correlation functions in the microcanonical ensemble. And that statistically correlation functions in the microcanonical ensemble look like correlation functions in the canonical ensemble. So up to 1/n connections, you believe that not only these correlators inside the thermal state, but also these correlators taken in a generic pure state in the CFT. And this will be important because now I'll start talking about pure states, have the same form that they have in a thermal trace. So this is something that comes just by saying that these modes of these fields that you have obey the standard axioms of statistical mechanics. They look the same whether you use the canonical or the microcanonical ensemble. They look the same whether you use the microcanonical ensemble or a generic pure state. So this is an assumption. But as I said, okay, so you can.
So these EA dagger guys are defined as the coefficient of the plane wave modes, which look like plane wave modes near the horizon.
Correct.
On the other hand, these properties that you were saying, eigenstress normalization, etc., These are more like modes of the boundaries here.
Correct, but these
Which
guys
would be
are
like
linearly related to the boundary modes. These A omegas are related to the boundary modes with some factor, which is C omega beta. So if you assume that all of these properties hold for the boundary fields, then they also hold for these E fields. Now the relation between the A and the omega is just divided by some commutator, but this is some number. It's a C number. So it's a number that depends on beta, but it's a C number. And so, this is just a linear relation. In fact, I should emphasize at this point, I might sometimes be a little schizophrenic about whether I use A or O, and the relation between these two is just this linear relation. Now it's not obvious by the way, so I should,
Yeah, this is not obvious at all.
Why is what not obvious?
The relation between O and omega done this way,
Between O and A done this way.
These modes, as they go to R going to infinity, how do they look like?
As they go to R star going to 0 in this tortoise coordinate, they go back to the O modes. You see, there's a prediction that you get from AdS CFT, which is the following. It's an AdS CFT prediction. If you take modes that are normalized in this way near the horizon, then the coefficient of this wave function at R star equal to 0 has to be the square root of C beta omega. So if you wanted to compute the commutator, one way to compute the commutator would be to take the ratio of the value of the wave function near the horizon to the value of the wave function near the boundary. And that has to be this root of C beta omega. So if this doesn't work out, then we would have a problem. But it does work out. You can check, for example, in two-dimensional CFT that it does work out. So if you come back to some other report.
Certainly, we can
Small
clear. It's called.
So this is not for free. If it wasn't the case that the ratio of the wave function near the boundary and the ratio of the wave function near the horizon was the same root of C beta, then you would be in trouble. Then this map would not work. But you can check in some cases, in particular about BGZ, by doing a quantization about BGZ. You can also compute these 2-point functions exactly using model invariance. That this does indeed work out. And in general, it's a prediction that it will work out all these. Okay. Good. So now let me say a little more. Sorry, I'm going
Can you go back to the last slide?
Yeah.
So this against it, this termination hypothesis, okay. There are some versions of it. Some involve time erasing and all this. Right?
It's a very simple hypothesis. Actually, it's just a statement that you look at some operator.
But you have to time erase it.
Huh?
You have to time erase it or something.
But it's eigenstate summarization hypothesis in the sense I'm using it is this is the following statement.
Okay.
It's a statement that you take the matrix element of an operator O inside two eigenstates, you get some diagonal term which is a smooth function of energy, plus some off-diagonal terms, okay, which are some smooth function multiplied with some erratic phases, and the key point is that the average magnitude is e to the minus s by t. It's actually, it looks like something deep, but it's actually very simple. It's just a statement that the eigenstates of the Hamiltonian operator, which are the energy eigenstates, don't have any nice correlation with the eigenstates of the O operator. And this is kind of true. The moment you turn on any interaction, even if you take simple harmonic oscillators and you turn on a small interaction, in general, you might have had some free energy eigenstates which look like number eigenstates, but the interacting eigenstates are totally mixed up versions of those. So then number eigenstates scrambled with some random unitary. And the moment you do that, you get some form of this kind. That's the only sense in which I'm using this.
But for that, actually, you need some time erasing.
You need some time averaging in what sense? It's a true statement that if you take a generic pure state, if you pick up a pure state using the Haar measure of the set of states, so you can take the microcanonical set of all states in some energy band. You can take the Haar measure of that. You can pick a state using the Haar measure of that. It's true that a generic state picked in this way has the same correlators as those in microcanonical and so on.
This becomes an averaging over the matrix elements of O. Some over many matrix elements.
Yeah, but this hypothesis has some version that I remember correctly.
This is certainly there.
This is
a stronger one, I would say. Yeah.
Good. Okay. This is all I'm using. This is not particularly strong, I think. And after this, the state psi is some arbitrary linear combination of energy through the Haar measure. Okay. So I'm going a little slow, so I have to go a little faster than this. Okay, so now the claim is, to describe, now I want to ask what happens inside the black hole. So I'll give you some answers to what happens outside the black hole, what happens in empty AdS. Now I want to ask what happens inside the black hole. I'll make this precise in a second. Let me just give you an intuitive sense. When you quantize a field, you have to have both left and right movers. Okay, left and right movers in this sense, right now refers to time and just the radio reporting. So there are, near the horizon, as I said, things become like plane waves, but there's a left mover and there's a right mover near the horizon. And you have to do the same thing behind the horizon. Okay, so this is near the horizon. So this big brown layer is the horizon. Now the thing is that outside the horizon, the left and right movers are actually linked by what happens at the boundary. So they're the same modes. Remember that had to do with the phase I had in the previous setup. It was E omega m into EI omega t minus r star plus e to the I delta into t plus r star. But behind the horizon, you don't naively have any such boundary condition. You could put such a boundary condition, but whether or not you put it, the fact is that you need both left and right movers behind the horizon, and these right movers, which are these blue guys, are naively they're independent of the modes on this side. So the left movers, which are these purple guys, are linked to the purple guys on this side of the horizon, and that's just forced onto you by the infinity of the field across the horizon. But these right movers could be independent. You could link them by putting some boundary condition deep inside the interior, but naively they're independent. So these blue and these red guys are independent. These purple guys outside are the same as the purple guys inside. And these right moving modes are the modes that Hawking analyzed in his paper when he was talking about these modes that bounced off the origin of polar coordinates by doing ray tracing rays all the way from square minus. These were the modes he was talking about, these blue modes. You could also think of these modes as coming from the left asymptotic region of an internal black hole. If you had an internal black hole inside the middle of the horizon, inside the interior, you would have some modes that came from the right boundary, some modes that came from the left boundary. These are like modes that are coming from the left boundary. So this is how you should think of them intuitively. Let me say something more precise. You see, the thing is that you want that a bulk field, whatever bulk field you write down, should have the right short distance correlators. This is almost a defining property of a bulk field propagating in some space with some metric g mu, which is that as you take x1 goes to x2, in particular actually I take the distance between these two to be much smaller than the curvature scale, which is dependent on the temperature of the geometry. You want that this correlation function should behave this way. And this is kind of a defining property, so it's one of the properties that we want from this. And it's kind of a defining property. And now you can ask, you can translate this to Kruskal coordinates and try and ask what happens near the horizon. And you can actually see quite easily that from demanding that there's a right short distance behavior of these bulk fields, if you look at the correlation function of the following kind of object. Now there are these u and v light cone Kruskal coordinates. So you have to take the derivative of field with respect to u and also take them on the same v light cone. Take them on the line of constant v. You can check that if you do this, and if the field has this property on top, then you find that in this limit, the field has to have this property. Okay? It looks like 1 by u squared, delta u squared, and it becomes ultra-local in these transverse directions. Okay, so this delta function, this is called ultra-locality. That the field happens to have correlators only when the transverse directions are exactly equal. It's something that you might have seen in these recent papers by Busso and Wall and so on, and this, trying to prove this holographic mount. But in any case, it's just a simple property of two-point functions, which you can derive. The second line follows from the first line. Okay? And so this is the property that you want for fields, and you want this property to hold not only outside the horizon, but also across the horizon. So you want this property to hold. If I take a V ray that cuts through the horizon, you want this property to hold for correlation functions. It's a precise property that you want. And you can Fourier transform this property to ask what properties do you want from these modes that the field was made up of. So this is a property I enclosed in position space. You can Fourier transform it to ask what properties you want from the modes. It turns out the properties you want from the modes are this. You want that these tilde, these right moving modes, these new modes that I introduced, have to first of all have the same correlators, 2-point correlators with themselves that the ordinary modes had. They have to have a unit commutator with themselves. I didn't impose only the 2-point function. I also imposed the fact that they transform correctly under diffeomorphisms and are local. So these commutators actually come from there. But the 2-point function that I wanted gives you condition 1 and condition 4, which is that they have to be entangled correctly with their conjugates, and have to have this 2-point function, and have to also be entangled correctly with the guys without a tilde. Okay? So notice here you have an A tilde and you have an A, okay? And these are two different guys. An A tilde and an A, and these two have to be entangled correctly.
A tilde was the right mover.
A tilde was the right mover outside the horizon, inside the horizon, and A's were both the left and the right moves outside the horizon, in particular also the right move inside the horizon. And these conditions 1 and 4 just come from demanding the 2-point correlator I had previously. these conditions, come from demanding canonical commutation relations of the field, and the fact that it transforms correctly under large diffeomorphisms. This third relation, and that's related to this gauge I chose in the beginning, which was that I chose gauge by fixing a point on a boundary, and you know how the Hamiltonian transforms down some points on the boundary. It just moves points on the boundary by time. And that tells you the commutator of this inside mode with the Hamiltonian has to be this. Notice actually there's a sign here. Usually annihilation operators have negative energy. This guy has positive energy. So the annihilation operator behind the horizon has a wrong energy sign. So this is something that you might have encountered anyway in analysis of Hawking radiation. But it just comes from an analysis of the behavior of these fields under large diffeomorphisms. So you want, just by Fourier transforming how canonical commutation relations behave under large diffeomorphisms, the corrective point function, you find that you want to find modes that have all of these properties. Okay, and actually from now on, just a notational point, I'm going to drop this M index because, as you can see here, it's just a spectator, it doesn't do anything.
Sorry, how does the commutator follow?
This one?
Yes.
This just comes from demanding actually canonical commutation relations. It's a little bit like a normalization. It comes from demanding that, phi into phi dot inside the horizon at correct value of r star is delta of t minus t prime. Demanding that on the same tortoise coordinate, which is what's giving you the time inside, phi dot, the commutator is delta of t minus t prime.
So it's an equal life form, equal life.
No, it's not equal. It's just equal time. You just quantize the field on equal r star. Just quantize the field in equal r star, and t is the spatial coordinate inside the horizon. It's just equal time commutator, not equal life form. I mean, it's just demanding that field, commutes its space-like separation. There's a normalization.
So what tells you what choice of time to make?
What tells you what? It actually doesn't matter, right? I mean, you can choose. So the main thing that you want here is the thing should commute its space-like separation. Then there is some coefficient in front that could tell you, how things vary with time. The fact that things commute, the equal time commutation relations are just saying at equal time the only things that are not space-like separated are things which are bang on top of each other. So that's the main thing that you need. That fact is independent of what choice of time coordinate you make.
So you're saying with the choice of r star as time, this normalization is what it is.
This normalization. Okay. Now,
Okay, this tilde and then a tilde and a. Okay. So
there's
okay. So del m prime. Okay, on the other side. Okay. Can I relax the condition that m is equal to m prime in the?
I think not. Otherwise, you'd start violating, invariance of the Schwarzschild black hole under just rotations of the boundary. So you can't relax it.
Why do you demand this in typical states?
Why do you demand this in typical states? Because of what I said, earlier, you want typical states to have the same properties that thermal states do. So you want a typical state also to look like an empty, like a Schwarzschild black hole.
But I could have demanded these in thermal states as well, which
I
actually do.
Demanding this in typical state is stronger than demanding that it's true in a thermal state.
That is right.
Yeah.
Okay, so then I can say in terms of so m equal to m prime. Okay, for the last equality. Okay, I can say that it's a property. Can I say that it's a property of psi, or can I say it's fixed by the Bogoliubov transformation?
No, it's a property of psi. It's a fact that you can say it's a property of psi. It's a fact that
So it doesn't restrict the Bogoliubov transformation.
No, it's a fact that you expect that. Well, you're right that it's a property of typical psi, which has the property that you can rotate it without changing bulk quality. You can make rotations of the S3 and the boundary without changing. These M's are the modes of the S3 which you can rotate.
Yeah.
Things are general rotation. Okay, now, so what's the central paradox? The central paradox is that there's this claim from ANPSS, which is that these A tilde omega operators cannot exist in the CFT. So this is the claim that I want to discuss. So as I said, I've been trying to make things and outline my assumptions and try and make things as precise as possible. And this is the claims. Okay, so now let's see. I'm going to try and outline this claim, and I'll try and outline some counter arguments and then some recent passes. Okay. So let me just give you a history, because some of you have seen this in various sub-tasks. There was a strong subadditivity paradox that people came up with earlier, which is what led to a lot of attention, and many people focused attention on that. In fact, it's the weakest, I think, of all of these arguments by far. and it's but it's an interesting argument because it led to the whole thing. In fact, it was first pointed out by Mathur. There is this paradox which has to do with strong subadditivity, which if you translate into operator relations, really is the same thing, that E tilde doesn't exist. I won't describe that paradox. But then there were some additional arguments using some properties of what kind of commutators you would want the A tildes to have with the A's, and how those commutators would typically be large. And what's called the occupancy paradox. This is the only one I'll discuss. And then there was another paper by Maros and Kojinski, which tried to argue, again using the same. By the way, if you read these papers, the language that they're using is somewhat different. They're not trying to argue in terms of this non-existence of operators. I'm rephrasing everything they're saying in what I think is what I prefer, in the language I think is more precise. And so they have these additional arguments saying that these, based on the fact that these typical Schwarzschild number eigenstates are approximately energy eigenstates. And maybe I'll review this argument in tomorrow's colloquium. So I'll review this one and this one. And then there's a more recent paper, which I'll talk about at the end. I'll describe this argument. But this is just to give you a history that there's been a lot of work to try and make these claims. Okay. So let me try and tell you one of these, which is called the occupancy paradox. It goes as follows. I wrote everything in terms of E tilde, but let me work in terms of O tilde. There's only a relation of a commutator between them. Now it says, let's look at this commutator of O tilde with O tilde dagger. Okay. So now I calculated the generic state. Remember, we've been saying so far generic states are the same as correlation functions in a thermal state. So I do correlation functions in a thermal state. So this R should actually be here. It should appear later, but it's traced in the right CFT. But anyway, traced to the right Hamiltonian. And this is the same as some correlation function where I commute this. I use the cyclicity of the trace to take the O tilde on this side, okay, and then commute it through the Hamiltonian, which makes me pick up another factor of e to the minus beta omega, and then I use back the equivalence of the thermal trace with typical pure states to come back to this. Okay, so this seems to give me a relation for O tilde and O tilde dagger, and O tilde dagger and O tilde. And I've outlined what I used. I used the equivalence of microcanonical and canonical, and some build cyclicity of the trace, and the commutator with the Hamiltonian, which is something I demanded at the beginning. But now, if I demand also that O tilde behaves like an annihilation operator, and O tilde into O tilde dagger is some number, which is that C number that I mentioned in the beginning, but it's some positive number. But if you use this here, you will see that if I combine this and this last point with this, you will find that this expectation value is actually smaller than 0. Okay? And that's clearly observed. How can it be that the expectation value of a number with its adjoint is smaller than 0? And this is actually just a statement of the fact that an annihilation operator, which has a commutator of 1 with its adjoint, can't at the same time have positive energy. It's the statement that if you have annihilation operators and they have positive energy, that leads you into paradoxes of this kind. But it's really a paradox it's very simple to outline this paradox. You take this, use cyclicity of the trace and all of this, use the fact that O tilde behaves like an annihilation operator, and this suggests this. By the way, when they wrote it, they talked about how there's a lack of a left inverse and so on. But really, this traces everything in terms of 2-point functions. So it's a retracing of the argument that this was made in the EMEFS paper with Stanford. So it looks like we have a problem, and this is clearly not only not what we wanted. Remember, we wanted this to be 1 by 1 minus e to the minus beta omega, but in fact, it looks like it's something absurd. And so maybe these O tilde operators don't exist in the CFT. How can you have annihilation?
The second last equation was the dagger in the wrong place.
This one? This one?
No. The second last equation was the last equation.
This one?
Yeah.
Which one? This one?
That to that.
This to this?
Yeah.
So you see, if you put in the fact that O tilde and O tilde, let's set this to 1, for example, and now put this here. So use this 1 to commute this O tilde dagger on the other side. Okay, so now you've got, psi, O tilde dagger is e to the minus beta omega, plus e to the minus beta omega into this guy here. So now you put everything back together. So you see you get from here. So let's say this is minus 1. So what you get is psi a omega tilde dagger. Psi is e to the minus beta omega into minus 1, okay, plus the same correlator again. Right. So if you solve this for e omega or e omega tilde, you will find that it's minus 1 by 1 minus e to the minus beta omega. And that's a problem. So okay, that looks like a problem. How did this happen? So there are many such paradoxes, and you might have thought that these paradoxes appear only for generic states. So maybe generic states have a problem, but the thermal state is good, and maybe the eternal black hole at least is good because we think we understand the eternal black hole well. But I want to say that these paradoxes occur not only for generic pure states, but they also extend to the eternal black hole and the thermofield double, which we think we understand well. So it's not like you can get away by saying, pure states have some problem, but generic states, thermal states or mixed states or the eternal black hole is correct. And so let me try and outline that. I'm going extremely slow, but let me try and go faster. So let me remind you, the eternal black hole is dual to this entangled state of two CFTs. Okay, so this was proposed by Madhasen in 2001. So it's the eternal black hole, which is this geometry which has two asymptotic regions, is proportional to this thermofield double state, which is the state with energy eigenstate in the left entangled with energy eigenstate in the right, with this e to the minus beta e by 2 factor. The only thing I want to emphasize is that there is a Schwarzschild time here, which is the killing time that performs rotations about this bifurcation point in the bulk. That's identified with the boundary time on the right, but it's identified with minus of the boundary time on the left. Okay? So the CFT time on the left runs as minus of the Schwarzschild time. In particular, CFT time on the left actually runs up on both sides, whereas Schwarzschild time runs up here and down here. Okay, and this is something, it's just a property of the geometry. So now what I want to do is I want to consider these time shifted states to try and tell you how this paradox appears here, which correspond to taking this and translating this to either the left or the right Hamiltonian. They actually both give you the same state, and this gives you these energy eigenstates but with some additional phases added on. This is actually a subset of states that were considered by Gautam and collaborators in the context of AdS3. This is a small subset of those because it just involves translations with the Hamiltonian. And now actually we understand what these states are pretty well in terms of their geometry. You might have thought, I translated it to the Hamiltonian, I added some phases, who knows what happens to the geometry. But in fact, you know what happens to the geometry. The geometry, a time translation with the Hamiltonian corresponds to a large diffeomorphism in the path. That's something we generally understand about gravity, that translations with the Hamiltonian correspond to large diffeomorphisms. So this e to the IHLT is just large diffeomorphisms that die off at the right boundary, but that don't die off at the left boundary, that move the left boundary up and down. That's what this e to the IHLT is. We understand this geometric action. So for example, this is what such a diffeomorphism might do. It might move a nice slice that runs from right to left boundary in this way to another nice slice that runs from right to left boundary in this way. It doesn't move the point in the right boundary, but it does something to the point in the left boundary. But of course, this is a particular picture I drew. The extension of this diffeomorphism into the bulk is not unique. For example, I could have, in terms of these Kruskal coordinates u and v, I can define some Kruskal coordinate that does this. X equal to 0 is a line in the middle. So x is u minus v. So this is some transformation which implements a diffeomorphism of this kind. But this is a particular diffeomorphism I wrote. I could have written some other diffeomorphism which would do the same thing. And in fact, I can use this. I can use this freedom that all diffeomorphisms, large diffeomorphisms that differ by trivial diffeomorphisms are really equivalent. That you have to mod out the bulk theory with that to undo this diffeomorphism everywhere except for the left boundary. Okay? So really, all this time translation is doing is it's leaving the geometry, bulk geometry invariant, but it's gluing the boundary theory differently. Now remember, in the beginning I said that the boundary theory was glued by saying T left is equal to minus of T Schwarzschild. What this left diffeomorphism is doing is giving you the same bulk geometry, but with the boundary glued as T left is equal to minus T Schwarzschild plus a shift, which is this capital T. That's what it's doing. And now you can see that these states are therefore also smooth, but they are glued differently to the boundary. So we understand what these states do on the boundary, we understand what they do in the bulk. Okay. Now, the next statement I want to make is that these states are, for making the statement, all I used was a relationship between Hamiltonian translations and diffeomorphisms. I didn't use any equations of motion. So I would actually expect this to hold for arbitrarily long times, including times that are exponentially large. And you might worry that I'm using the geometry to make a statement of this kind. But really, there are two other things that would make you believe that these states are smooth for arbitrarily large shifts. One of them is that, from the right, making this left shift physically corresponds to just getting the right observer to jump in at a later time. Now, what happens to this? What happens if the right observer jumps in at time 0 in one of these shifted states is the same using the isometry of the thermofield double under time shifts to ask what happens to the right observer if he jumps in the original state at a later time. And we believe that that experience is time translationally amazing. And secondly, in the end, what was it that told us to choose the phases to be 1 and 1 on both sides? So that's just a choice of time on both sides. if I choose a different, if there's no notion in which I can choose a common origin of time on the left and the right CFTs, so if I just choose a different origin of time on the left CFTs, then I would have been led to the statement that the eternal black hole was dual to the thermal field with some of these phases. So really the fact that you set the phases to 1 and not to some arbitrary number has to do with the convention of choosing a certain common origin of time on the two boundaries. And that's an arbitrary convention. And therefore these time-shifted cousins of the thermal field state, they are distinct states in the Hilbert space, but they should really be treated on the same footing, unless you want to say that there's some principle in the world that tells you how to choose time origins in some common way. And we don't believe there's any such principle that tells you how you should choose time origins in a common way. And therefore all of these time-shifted states should be treated on the same footing, including time-shifted states which are shifted by exponentially long times. Why is this exponentially long important for me? Well, sorry, before I say that, let me just say, what do I want for these O tilde operators? These O tilde operators that I described previously in the single-sided case. I want actually the same properties. In particular, they should have the wrong energy under the right Hamiltonian. And the reason they have to have the wrong energy under the right Hamiltonian is because I'm asking what is happening to an infalling observer who falls in from the right. Okay. So these guys actually need to commute with the left Hamiltonian because they don't care about large diffeomorphisms that act only on the left. But they have to have the same commutation relations with Hamiltonian on the right. And they have to have the correct correlation functions, which is in all of these time-shifted states as well. Okay, good. So now let me just do some more analysis. Remember, I said let me take any operator x. Let's say I have some operator x, and I want to take a long time average of the expectation value of x in all of these time-shifted states. So psi t is the thermal field state shifted with the left Hamiltonian. Which is simple algebra. It takes you to the average of the states taken in energy eigenstates. So there should be a sum over E here, plus some cross terms. Okay. But these cross terms actually all die out if I take a long time average. So if I'm allowed to make shifts which are exponentially large, and all of these cross terms die out, and in fact I'm led to the conclusion that these properties that actually I demanded hold in the thermal field state and all of its time-shifted cousins actually have to hold also in energy eigenstate pairs. Okay, so these properties that I wanted to hold initially only in these thermophile states to demand that all those horizons are smooth should also hold in these eigenstate pairs. And that I get by doing these long time shifts and taking a long time average. Now I'm going to make an additional assumption. So I just wanted to outline all the assumptions I make here clearly. The additional assumption is that there's no wormhole in eigenstate pairs. Now if I have an eigenstate pair in which there's no entanglement, I just have one CFT.
So in your last slide, where the choice of long time, where did that go in?
Choice of long time went into saying that whatever these expectation values are, these cross expectation values, if I take this time to be exponentially large, then I kill them. Unless I want these cross expectation values to be exponentially large. The long time went into killing this term. Okay. So now I say, I have some eigenstate pairs, and these eigenstate pairs shouldn't have a wormhole between the left and the right. Now the eigenstate pairs don't have any connection between the left and the right. It's one CFT in one eigenstate unentangled with another CFT in another eigenstate. Therefore, I should be able to do whatever unitary transformation I like on the left, and it should not affect the experience of the right infalling observer in these eigenstate pairs. So this is called the no wormhole in eigenstate pairs hypothesis. Some people would question this. So Marolf and Wall, in fact, question this. I'll come to that a little later. And now you can actually set up a version of the occupancy paradox once again. This is exactly the same slide as before, but now phrased in a two-sided case. Now I can use this unitary to just convert the left CFT, put the left CFT in the vacuum all the time. And then you end up back with the same paradox. See, this is exactly the same slide, except that instead of psi, I have omega e here. So I have a two-sided state here. And therefore you are led to the conclusion that even in the eternal black hole and its time-shifted cousins, there is no operator O tilde that would ensure that all of these states are smooth. So it's the same paradox, but the paradox appears also in the eternal black hole. Okay.
But do you have an eternal black hole when there is no entanglement between the left and the right?
No. So that was the assumption that I made in the at the last assumption I made, which is that there's no entanglement and there's no eternal black hole.
No eternal black hole.
There's no wormhole between the two. So there's no wormhole in something which is not entangled. So that's one of the additional assumptions. Okay, so now I want to go through this a little fast since I've given some number of talks here. So let me describe a proposed resolution and then I'll come to some outstanding puzzles. So this is a resolution So one of the resolutions that we proposed for this was that these paradoxes are arising because you're ignoring the limitations of bulk effective field theory, and you're ignoring the fact that really what an infalling observer can measure are some finite polynomials of these single trace operators, and he doesn't have the ability to measure arbitrary observables. Now, what the infalling observer can measure are some polynomials which have some correlators with some number of insertions and some maximum amount of energy. So each of these insertions has to have an energy less than n. The total number of insertions has to be less than n. So this is it's not quite an algebra because it doesn't, if you multiply two things, you might run out of these bounds. But it's a truncated operator algebra. Okay, so now the claim is that corresponding to this, maybe I'll say this again in a little more detail tomorrow, but let me just try and give you the outline now and come to puzzle since I'm running a little bit out of time. Corresponding to this, the claim is you take a certain state psi and you define a little Hilbert space about that state psi. The little Hilbert space corresponds to taking all of these polynomials that are measurable, all reasonable experiments that you can do, and exciting the state psi with all of these reasonable excitations. And since the set of all these reasonable excitations you can make is dimensionally much smaller than the full Hilbert space, which is just a statement that you can measure only a small subsector of operators in the full Hilbert space, then it tells you that if any of these operators annihilates the state, that means that this operator has to be 0. Okay, so for a generic state, if I give you a small subset of operators and I give you a generic state, in general the small subset of operators, you will not be able to find anything that annihilates the state. You can easily check that the set of operators that are annihilated by A alpha, the set of states that are annihilated are the set of codimensions, a very large codimension. And therefore this little Hilbert space is actually isomorphic to this truncated operator algebra that I mentioned. And then the claim is that given some generic equilibrium state, you can define this antilinear conjugate map, which basically takes a state in this little Hilbert space to another state in the little Hilbert space. This map exists because of the property I mentioned previously, that none of these guys are 0. If one of these guys was 0 and omega dagger was not 0, I would have a problem in defining this antilinear map. And this map is actually the same map that appears in some branch of mathematical physics. It's called the map that appears in this two-meter Takasaki theory of polynomial algebras. But related to this, you can define these mirror operators in this way by taking this map, putting in some factors of the Hamiltonian. And the claim is that about each state you can define these mirror operators in this way. Okay, so now, and then the claim is you take these mirror operators, you smear them with these mode functions that I mentioned previously, and you look at correlation functions, and you do get the correct correlation functions that you want from semi-classical effective field theory. And this is the same. This statement is the same as the statement that these operators O tilde that I defined meet all the conditions that I imposed previously. I imposed some conditions on two-point functions and commutators, and the claim is that the operators defined using this map and with this factor of the Hamiltonian. It's not immediately obvious from the definition, but it's true that they do meet all of these conditions. Okay. Now, how did I impose this impossibility theorem? Now, the impossibility theorem was evaded through this notion of state dependence, which is the statement that if an observer falls into this black hole in this microstate psi, and the correlators, the field operators that this observer measures may depend in some subtle way on what the microstate is. Okay? And the claim is that this paradox arises by imagining that local degrees of freedom are described by the same operators in all states psi. So let me just try and describe that in this specific case. Remember, I demanded that if I look at the commutator of H with this O tilde, it has to have a certain property. Okay? And I demanded that O tilde with O tilde dagger has to have a certain property. And this is true of the operators I defined. Okay? But you can't replace this correlation function with some trace of this kind. And the reason you can't replace it is because this operator is varying as you go across states. So if you take some basis, even if you take a basis of states, and you ask for the sum on this basis in all psi i's and basis of states for this 2-point correlation function inside this basis, that's not the same as the trace because this operator O tilde depends on on which state you were in. And therefore, since there's no globally defined mirror mode, you get rid of the paradox, which after all relied on being able to take a trace and then using cyclicity of the trace and other things. So if you recognize that this operator is not the same in all of these basis states, then you're able to get rid of the paradox. So that's the way in which you get rid of the paradox in this case. But I want to come to some more recent puzzles. But before that, let me just say this also resolves this problem in the eternal black hole. In the eternal black hole, it says that the operator that you need to use in the eternal black hole is very explicit because there's a certain subset of the Hilbert space you're looking at, which is a completely explicit subset. It's a one-parameter subset actually, which involves the thermofield double, which is a t equal to 0, and time-shifted cousins of the thermofield double. And the claim is you use one operator about the state t equal to 0, and after you move, you look at a state which is related to the original state by an exponentially long time translation, you have to shift to another operator. Okay? In fact, we can write down these operators explicitly. These operators are the following operators. You take the left modes, you Fourier transform the left modes, okay, and you have to insert some projection operators. Maybe I won't explain this formula in detail, but since I'm running, can I go on for 10-15 minutes more? Okay. But so let me just say that in the case of the eternal black hole, where we have an explicit description of the set of states we are looking at, let me just say something, not trying to explain the details of this formula. Where we are looking at the thermophile double and its time-shifted cousins, I can explicitly write down how these operators are state-dependent. I can write down a formula for how they depend on any given state. And it's a state-dependent formula, and you can check that it's the same as the formula that's obtained by doing this map addition. I can explain this formula in more detail, but let me just make the point that you can carry out this program explicitly. Okay. Now, I want to say that this description can be used to solve also these other paradoxes. This occupancy paradox, this any not equal to 0 paradox of 2013, this Mallows fulgency paradox, and these Strong's validity paradoxes. And actually, I'll try and describe in tomorrow's colloquium how it also gives a certain precise description of what's called ER equals EPR conjecture, this relation between entanglement and workloads. I'll come to that tomorrow. But let me try and say, oh, sorry, before I come to that. So I'll say that. So this I'll say tomorrow. Okay. Let me say a few things about state dependence. Okay. So the first thing is that the state dependence is, it's unusual because you're saying that you're asking a question about what the infalling observer measures, but you're saying before I answer that question, you have to tell me what the state of the CFT is. But in fact, it's something that's appeared in other setups in AdS CFT, and this is something I want to emphasize because there's been a lot of discussion in the literature about the state dependence of our proposal. But without the, I think, broad realization that this is something that's appearing all over the place in AdS CFT. For example, there's this Raju formula that's used very commonly, which says that the entanglement entropy of a region, is related to, the area, minimal area surface that you can write down, which is bounded by that region. But in fact, it's, as all of you know, the entanglement entropy is not an operator. Neither is it the expectation value of any linear operator. So maybe all of you already know this, but let me just remind you, it's very easy to prove this. So let's say you had a Hilbert space, which is a direct product Hilbert space of H cross SB. And let's say there was some operator x, so that the expectation value of x give you the entanglement entropy of A in a state of this type. Okay. Now, the entanglement entropy is always positive. Therefore, this operator x is a positive operator. All of its eigenvalues are either positive or 0. But now consider some direct product basis of states, okay, which is not entangled. In this direct product basis of states, the expectation value of x is 0 because the entanglement entropy is 0. Therefore, the trace of x is 0 because this is the basis of states. But this means x is 0. Okay, that means the entanglement entropy is 0, which is of course absurd. So therefore, there is no operator x whose expectation value gives you the entanglement entropy. But in the sense in which I'm using here, in which I'm saying geometric quantities are observables, the area of a minimal surface is an observable. Okay, it's a metric is an observable, the metric at all points is an observable, then the area is an observable. Whereas the entanglement entropy is clearly not an observable. You can prove it's not an observable. So this is also a formula that can, if it holds, either the formula is wrong, but if it's right, then it can only hold in the neighborhood of states in some state-dependent fashion. There's a version of this formula by Jeffries and Josephine Su that actually says that the area operator is equal to the modular Hamiltonian. It's not a formula for between C numbers. It's a formula that relates to operators. And that formula is also explicitly state-dependent. Okay, so this is it.
So does this mean that entanglement entropy cannot be measured in an experiment?
Actually, given a single copy, you can't measure entanglement entropy in an experiment. You see, any function of correlation functions in the end is measurable if you give me infinite number of copies of the system in identical states. But if you give me a single, if you ask, is there some pointer I can couple that will directly measure in one shot the entanglement entropy? The answer is no.
But even expectation values of Hermitian operators can be measured in one experiment.
Expectation values cannot be measured in one experiment.
But this is somehow worse than that, right? Because it's not the expectation value.
It's not. It's that's right. So this is not. It's a function of expectation values of any operator. It's not the expectation value of any operator. It's worse than that. It's worse than that. I don't have a good sense. You maybe want to say how much worse it is, and I don't know how to quantify it.
okay, but naively, okay, like in 2D CFT, I mean, like it's defined by 3 operators. I mean, it's correlation function.
No, it's a correlation function in some enhanced space. So you use some replica trick and so on, you put some correlation function. In the original theory, there is no expectation value that gives you. This proves that there is no expectation value.
Actually, in a gauge theory, I suggest you can't measure the entanglement entropy at all.
Okay.
As defined by the replica trick. But anyway, that's another issue. But it's certainly only defined in an asymptotic sense, only with n copies a little larger in the bed. It's actually a little.
Right. So there are other issues that anyway have to do with entanglement, how to define entanglement entropy. And those issues may in fact even be relevant in gravity where situations may be even worse when you're talking about locality. But in any case, even simplest theory, when you have a direct product set of just qubits, there's no linear operator. And so this, if it's correct, is a state dependent. Even this modular Hamilton people talk about is not an operator in a traditional sense. Okay, this is one thing I want to emphasize. But let me go on to some recent puzzles. Yeah. Just in time.
What?
I'm
really sorry. Can you just recoup the last 1 hour?
No, it's actually we're perfect time. Because you heard everything. So yeah, perfect. Good. Yes. Yeah.
So, what is the observable status of the area?
But, if you believe that the metric is an operator, the area is an operator. So it's an operator. You might say the metric in the bulk is not an operator in the CFT. It's only an operator about a given state. But if you believe that the metric in the bulk is an operator, then it's an operator. Okay. So here's some recent puzzles. So now this is actually, I'm going to have to conclude by not giving a sharp answer, because I want to describe this recent Malolfin-Polchinski paradox, to which actually we don't have a clear answer yet. But let me describe it because I think it's very interesting. So what Malolfin-Polchinski said was, they were trying to take advantage of the fact that you can have very low energy excitations near the horizon. So they said, let's take a typical state and let's consider the expectation value of this operator G after having excited this typical state with this e to the I theta n. What is n? N is this. Remember, I defined these A and A dagger operators in the beginning. So you take this A and A dagger and you smear them with some functions f. Now f is a sharply peaked function. You can take it to be a Gaussian, but it doesn't matter precisely what it is. It's some sharply peaked function. So this n is like a number operator. Remember, because this is taking A omega, smearing it a little bit, A omega dagger, smearing it a little bit, multiplying them together. So it's a number operator. This G is a particular integrated 2-point correlator in the bulk. Okay, so this correlator here I've suppressed everything except for the Kruskal coordinates U. But I have to take some right-moving Kruskal coordinates inside and outside. I have to integrate them with the Fourier transform of this guy. So if you take this to be a delta function, I have to integrate them over infinite distance in the bulk. So you don't want it to be a delta function. You want to take a spread of this, which is roughly smaller than 1 over log n, which lets you get enough space to be able to measure this integrated 2-point correlator. And then the claim is, look at the expectation value of this operator inserted in the typical state excited with this number operator as a function of this theta. Theta is just a parameter that I put here. Okay. So it's a well-defined question about expectation values of 2-point functions in typical states that are excited with a well-defined operator. Okay. Once again, I'm paraphrasing that thing a little bit. This is not quite how I phrased it. This is, I think, a good enough way to phrase it. Good. Now the claim is that you can ask how much does the energy change under this unitary. You can compute that. It depends a little bit on how precisely you define the width of this function f. But it's not hard to see that the energy changes by theta squared into delta omega squared, where delta omega is the width of f in frequency space. It's got disconnected.
I'm going to show that operator.
Yes. Have you got disconnected again? So it's roughly n omega. It's a number operator of n. Of the Schwarzschild modes outside the horizon. But it has some finite width. So if it had been exactly n omega, it would not have changed the energy at all. But it's not exactly n omega, so it changes the energy. In fact, by theta positive or theta negative changes the energy by the same amount. So you can see the shift in energy is theta squared. So it changes the energy by delta omega squared.
I'm really sorry, if it were exactly n, why would it not? It's the number outside, right?
Yeah,
in a thermal state.
So let's say it's A omega dagger. If this A omega is defined as integrating over all time, and this A omega dagger is also defined by integrating over all time, then by definition this commutes with the Hamilton. You see, if I do e to the I h t, this picks up in e to the minus n omega t, this picks up in e to the I omega t. So again, it doesn't change at all. Okay, but you can compute the change in this G. Here I made some assumptions about how this number operator, what the commutator of this number operator is with these A tilde modes. In particular, I assume that it vanishes. I'll question this assumption a little later. But let's say it does vanish, then you can compute the expectation value of G under these assumptions, and you can show that the change of expectation value of G is order 1. It doesn't have this delta omega suppression. So even if you have a very low energy excitation, you can make this operator change in some order 1 fashion. Okay? So why is this a problem? It's a problem for the following reason. Let me try and explain why it's a problem. You see this unitary, this e to the I n theta unitary, maps the set of states with energy E to states with energy E plus delta E. Okay, where delta E is what I wrote in the beginning. Now, dimension of the states He is e to the S E, that's just a definition of the entropy. The dimension of these states E plus delta E is e to the S plus beta delta E, that's the definition of the temperature. So there's nothing. But since this delta E is an order 1 quantity, actually it's much smaller than order 1, this energy is n squared. So I've gone from energy n squared to n squared plus 0.1. Therefore, the trace of this operator x in this big Hilbert space, the trace in this should be the subscript He, is the same as the trace in this Hilbert space, He of the same operator x. Okay, so that's just something which you expect when general statistical mechanics comes. You change the energy of your ensemble a little bit, but order 1 amount, you don't change the expectation value of an operator. But remember that some typical state in this excited ensemble, okay, just from that, just from the fact that the ratio, if I give you,
sorry,
yes,
really sorry.
Yes.
The trace of x
There should
is
be
the typical operator.
Yes.
In the bigger Hilbert space,
Yes.
is the same. Why is that? That operator has very little. You're interested in delta changes, right?
In small changes.
But x has not enough support in the.
No. It's just the fact that if you ask what is the entropy at energy, let's say x was say the entropy. You ask what is the entropy at SLE, what's the entropy at some amount where you change the energy by a small amount. The things don't change. Things only change by a small amount. So there are delta E factors here. But so let's say you ask for S by n squared, which is an order 1 operator. Okay. And you ask for what is S by n squared E plus delta. It changes by only a factor of 1 by n squared. Because you ask what is the pressure at energy when the energy of this room is some amount, n squared joules. Now you ask what is the pressure when the energy of this room is n squared plus 0.1 joules. It doesn't really care because it doesn't care about the energy is shifted only by a factor of 1 by n squared. The relative shift in energy is 1 by n squared. So relative shift of any index,
So delta E is order 1 over n squared compared to
delta E by E is 1 over n squared. In fact, it's small. It's only 1 over n squared. It also has this delta omega squared factor.
Okay.
So not only is it 1 over n squared,
it is 1 over n squared. So
it doesn't.
Okay, so that's the sense in which
those two traces are same.
Okay, now I'm with you. Thank you.
Expectation. Now, however, notice that the dimension of Hilbert's, if I take some operator in a big space, a typical operator, and I can make this precise by using the Haar measure, and ask what is the projection. So I have two spaces. This is this He plus delta E, and I have the space He, which is embedded inside He plus delta E by means of that unitary map. Ask what's the projection of a typical operator on this space onto this space. The projection is just the root of the dimensions. Okay, so if you ask what is the projection of some operator in this bigger Hilbert space on a subspace of a typical operator, picked using of a typical vector picked using the Haar measure in a bigger space or a smaller space, it's just the square root of the dimensions. That tells me that if I take a typical state, psi prime, then this typical state can be written as 1 minus beta delta E by 2. This is the square root factor. I've ignored the high order terms. Plus some square root of beta delta E into some orthogonal space, where this psi orthogonal is orthogonal to the set of states you get by exciting low energy states in this unitary operator. Okay? But that means that if I take any operator G, where G was my particular operator in the beginning, then the expectation value, remember now I have to use also the fact that typical state expectation values are the same as these traces of the ensemble, which is something I've said many times. And the change in the expectation value of this minus this is, can only come from here. And if this G is some bounded operator, okay, it tells me that, for a typical state, if I take a low energy excitation, it shouldn't actually change the expectation value of this operator G by some. Okay, so you can go through this in some more detail. There's a slogan. The slogan is that...
Sorry, just that last term, then What is lambda? Lambda G is the
largest eigenvalue of G. You see, let's now take an expectation value of G inside this state.
Yeah.
So you get some terms from here, plus you get some terms which are cross terms. These cross terms can only be as large as the largest eigenvalue. You see, at most it can be that G maps something here. The G gives you this operator. So the largest term you can get from the cross terms is this. Plus there are some other terms which are higher order. So for beta delta E smaller than 1, the expectation value in a typical state psi prime shouldn't be much larger than the expectation value in a typical excited state from the low energy ensemble by any amount larger than root of beta delta E. There's a square root factor you would have that.
So order 1 over n. So
oh no, this is root of beta delta E. It's not delta E by E. So here I was using the fact. So this is root of, remember delta E was delta omega squared into beta. So root of beta delta E is beta delta omega. When delta omega was at width and frequencies. So this thing can change, not by 1 over n, but it can change by some factor that depends on delta. Okay. There's a slogan for this. The slogan is that in a thermal system you should not be able to definitely excite a system with an energy smaller than kT. Okay. If you have a thermal system which is composed of many degrees of freedom, like this room, there is no way I should be able to definitely excite a system by exciting it with energy less than kT. And this is the statement. And the statement of the paradox is that black holes allow definite excitations to live near the horizon with arbitrarily low asymptotic energies because of the redshift of the horizon. So you can this number operator that they wrote, creates an excitation near the horizon, which you can measure by measuring the appropriate, integrated 2-point correlation function. You can measure it definitely because that's the statement that changes the correlator by not of 1 amount. But you can make the energy very small. And it's a factor of geometry. Geometry is telling you that you can have low energy excitation which an infalling observer can hit and measure, but at arbitrarily low asymptotic energies. This is the slogan, but there's a statement, more precise statement in terms of correlators.
These live within Planck scale of
No, they don't live within Planck scale. Well, to measure them, you have to measure this correlator. You have to measure this correlator, which is an integrated correlator, which involves taking the field and integrating it to the Fourier transform of this f. So if this f has very narrow width, 1 over delta omega, you have to integrate the field over some width which is inverse of that. So to measure this is not a correlator that lives in Planck scale.
If the excitation were anywhere order Schwarzschild horizon or out, then you would have no shift factors. It will all be thermal, and you will never get the low energy.
Right. So it's a little well. Okay. So
I'm just trying to understand.
Yeah, I agree. So it's true that if you think in terms of classical shock waves, you want excitations to live very close to the horizon. This thing is not quite a classical shock wave. It's something that's slightly more diffuse. It creates some. So you're right that if you think of it as something that's a shock wave, then it which is localized at some point, it has to live very close to the horizon to have low energies. But I don't know what a good classical way to think of this is. But it's certainly true that to be able to measure this operator, you have to fall through and wait for some time. If you just wanted to measure the operator outside the horizon, you would not be able to. So you have to fall through. You have to have some detector that falls through and that waits for some time. So I don't know a good classical way to think of it. The shock wave is a possible classical way to think of it, but it has the weakness that it suffers from the weakness and it looks like it's localized at some point. And that's actually a good intuitive way to think of it. But this operator, I think you don't have to think of things that are localized just like scale.
If you are willing to go past the horizon, then I don't know. Then it gives us a
this is a quantum excitation in some sense, and roughly you have to be able to measure enough of the field on the other side to be able to see the quantum excitation. I don't have a good intuitive answer to your question. Let me think about it more and see if I can give you a better answer. It's a good question. I don't have a good intuitive answer.
How much is the change in G?
It's order 1.
Delta Z.
It's just it's theta.
So actually, okay.
It's not suppressed. The theta is not suppressed by delta omega.
This. Okay, maybe it's not related, but there's a universality relation of Sumit Das and this Rothmeyer. If you bring it in there, it will depend on. If I just look at their formula, their formula depends on dimension and all this.
Sorry, I'm not understanding.
If I say that yours the operator that you're considering the operator you created is let's say it's created just prepared by doing some quantum points then the Sumit Das and Rothmeyer have some universality relation if I if they have relation with how much the energy change and how much the observable, okay, like say, del O, okay, change.
Yes. Actually, this is not in the paper, it's just something I'm presenting. But you it's a version of that.
This don't agree with their universal.
So there's nothing to, I mean, you can compute this n with h, you know the commutators of h with a dagger. And to compute this change in delta G, you have to know the commutators of h with phi. And that involves some assumption, but you can just compute it using these assumptions. There's no, it's just a free field computation. So you can do this computation.
Pretty sorry. But just if you can just go back, I just want to understand, these operators are bulk operators.
Bulk operators.
And the Hilbert space, because we are talking about infalling observers, the Hilbert space is, what precise Hilbert space is carried by an infalling observer?
Good, so good. So let me say a little more about that. Right now I'm saying, let's say there is some mapping between these bulk operators between infalling observer C's to the CFT Hilbert space. It has to be a very funny kind of mapping. That's the point we want to make. It has to be a mapping that's a very funny kind. So these are some operators in the CFT. I propose some map here, but let's say there are some operators, whatever the map is, and they have just give me a few minutes. I'll keep it. Okay. So now this is the problem. This is the way to understand the problem in terms of the slogan. The slogan has a difficulty, as Sandeep pointed out. So yesterday's excitations are very close to the Planck thing, but these quantum excitations get at some distance also. Okay. So now actually this suggests a little bit something that's slightly problematic also with our construction. And there are three alternatives. Okay? I think there are three alternatives. Maybe there are others. One of them is that there's some problem in effective field theory. The change in this correlator that you computed in some free field approximation is not correct. And actually these states don't have this quantum excitation. Even though you try to excite them, you fail to excite them. So you try to rotate the exterior without rotating the interior, you fail in that. That's a possible excitation. That's a possible solution. Another possible solution is that these states are excited, which is related to what Sandeep said. The mapping between the bulk and the boundary violates linearity in some significant way, but in an unobservable way, and that allows you to get rid of these bounds that I mentioned, which were after all bounds for linear operators. Or the third option is that the CFT doesn't describe the black hole interior. There's no black hole interior. There's no question of talking about these exciting this black hole interior. There's relatively mass there, but there's no. Okay, good. So now good. So let me try and describe these possibilities in some detail. So one may say, actually, I mentioned this also in the spring stop. Let me just say what we've negative things to report after that. You might have thought that, and without talking about all the 2-point integrated correlators, the naivest way to think about this Marov-Polchinski prediction, which is how it is in the paper, is you think of this number operator 1 tilde and 1 arm tilde, and you rotate it with this phase, and it gives you a factor of e to the I theta into this omega. Where do you have okay. Okay. So now you might have thought, now these correlators where you assume a certain commutator between the outside operators and the tildes do sometimes have problems. For example, in the eternal black hole, you might have thought that if you look at modes inside the horizon, and in fact many people did these right-moving modes inside the horizon, and you rotate them with the left Hamiltonian, that you would pick up a phase factor. But in fact, you don't pick up a phase factor if you define these operators carefully. That's important for ensuring that all of these time-shifted eternal states, are smooth. So it's important for doing that. And could it be that maybe you have to modify this commutator of the number operator with these operators inside, and maybe that tells you that this prediction of this phase is actually wrong. And in fact, you can see that the commutator of this number operator, even though it looks like a free field computation, actually has a problem. The problem it has is the following. If you think of this Marov-Polchinski operator, in the past it becomes very singular. Because what you're doing is you have a horizon. You're trying to send some excitation from here. But this excitation becomes more and more singular in the past. So if you form the black hole from the collapse of some infalling matter, then there's no regular solution that at late times has this Marov-Polchinski excitation. So there's a huge collision of this excitation that you sent from, it's an excitation you made in the future, but if you trace that state back to the past, which you have to do because you have to treat it like an autonomous state, and you have a huge collision with the infalling matter or whatever it was that formed the black hole in the first place, and therefore it could be that there's back reaction that modifies this commutator. And this is actually an attractive option because it's the most conservative thing if you could take this back reaction into account. But I have to say that this is something I've tried to do for some time, for a couple of months, and we have not actually managed to show why this commutator should be 1. And basically, it's anything you do, looks like if you try to guess an answer. First of all, doing this computation is hard. If you try and guess an answer, it looks like naively you violate either the locality or boost invariance of the geometry 3 times, either of which you want to modify. So I should say there are formidable technical difficulties in doing this. Maybe we are missing something. But this would still be, if you were to ask me, the most conservative and attractive option, which would be that these attempts to excite the states actually don't succeed by putting in arbitrarily low infrared excitations. You could at least add beta energy, 1 or beta energy to excite the states. Okay, now could it be, the other option is that these interior
operators. To understand what you're saying is, if at some point in the future it was a low enough excitation, as you go back in the past, because there's a sort of blue shift going in the past,
it has an excitation. There are 2 ways you can create an excitation. One of them is you modify the Hamiltonian, and h goes to h plus j phi. So you evolve with the usual Hamiltonian, and then you turn on a source at some time. That's one thing you can do. The other thing you can do is you can think of the state e to the I j phi into psi. The difference between creating the state in this way and this way is that in both cases the future after time t, if you turn on the source at time t, is the same. But this state is an autonomous state. So in this state, as opposed to the state which you created by modifying the Hamiltonian, the excitation has always lived. So it has to come from some regular initial condition. And this excitation you don't get from regular initial conditions in some nice way. So it has a problem. So there is some back reaction in the past, because if you trace it back into the past, and the past is nice.
But nevertheless, if you could have created a state at a later time in the first way, without being very close to the horizon. First of all, by being outside, and without having Transplanckian short distances involved and so on, it would be a sharp issue, right?
But this state you can create. So the state certainly exists in the CFT. There's no question about that. But the thing is that if you, maybe I'll say it on next slide. You want to compute now the correlator with this excitation made at this time. So this is this is time t, and this is time, say, t minus 1. This correlator that you compute actually involves making an excitation at this time, but measuring a field correlator across the horizon at an earlier time. Okay. So the reason it gets affected is because if you look at a state of this kind with a source that's turned on at later times, but think of it as an autonomous state, not as a state evolved with modifying the Hamiltonian, then you have to look at the entire history of the state. So the state was also different in the past. But this is a state which has some excitation near the boundary at this time. But if I ask what is the correlator of fields in a state which has an excitation near the boundary at a later time, the way I would do it is I would take this initial data and evolve it to the past, and then I would consider the correlator of these operators. On the other hand, if I just wanted to create this excitation, I would say I have a state which is just has no excitation till this time, and now I modify the Hamiltonian. But in this case, I'm not modifying the Hamiltonian. I'm considering an autonomous.
Sorry, I should go on, but I understand the difference between the two. I understand why the second way has this Transplanckian collision problem. But let's go to the first way, which, if you could pull it off, would not suffer from the...
Yes, but the first way also has no paradox. If you try to create the state in the first way, that integrated correlator actually doesn't vary at all. It doesn't change. It's not obvious in what I wrote, but it's true that the correlator I had to evaluate was a correlator where I was evaluating the fields in the past of the excitation. The way you can see that is because the fields, there's a u degree of freedom, and these are right-moving degrees of freedom. So right movers get influenced by things in the future. There are 2 ways. The only way you can influence a right mover near the horizon is by turning on an excitation in the future. Left-moving excitations you can send from the boundary. If you want to create a right-moving excitation, the only way to do it is by turning something on in the future. So in the second way of creating the state, which is by modifying the Hamiltonian, you would not have a paradox. The paradox arises only by considering the state as an autonomous state.
So isn't that suggested?
It could be suggested. It could be. Maybe this is right. So in fact, I was just about to say that. So could it be that these operators in the black hole interior violate unitarity barrier? And what that means precisely is, so maybe you're given 2 states with almost unit inner product, but you can jump into the black hole and distinguish between them. So the black hole gives you a way of distinguishing 2 states that almost have unit inner product. It seems funny, but because of just what Sandeep said, the problem is this correlator you have to measure to be able to see this violation of linearity is an out of time order correlator, and the bulk field is affected by a future source. So it's not an experiment that the infalling observer can do to detect this violation of linearity. In fact, there's a more serious problem, which is that the infalling observer has to be able to measure not only this state psi and its excited state with e to the I and theta, but also some. Remember, my argument was based on saying that there is some other state in the excited space which has almost unit inner product with this excited state of the lower space. But this violation of linearity is not observable for these two reasons. That first of all, this is an out of time order correlator which you can't actually measure because you have to make an excitation in the future and somehow inject yourself into the past to be able to measure it. And maybe also a single infalling observer can't actually measure. So Maroff and Policzynski have some words about how you can observe it, but really, the only way you can observe it is by either making some excitation. You can always engineer a future excitation if you are powerful enough at an early time, by acting as a conflict. So by doing something of this kind, and by giving the infalling observer infinite powers to be able to measure all states available space. So it's possible, but this certainly is a rather radical possibility, and it opens up the possibility of other problems if you're going to have this mapping that violates linearity in this kind of way. Okay, what's the possibility? This is by the way the first time I've said the word firewalls, I think, in this talk. The possibility is that there could be firewalls, and maybe the interior is always excited. So if it's always excited, then you don't have this paradox. You naively think you don't have this paradox because if it's always excited and you excite it some more, the generic states are excited, you add a little more excitation on top of it, and the infalling observer doesn't see anything different. But this is actually inconsistent with effective field theory. It's a problem with firewalls because of no-head theorem. And you can actually, in fact, turn the same Maroff-Policzynski argument on its head in the following way. Imagine that generic states psi have firewalls. You disturb them slightly at t equal to 0. This time in the usual way by just modifying the Hamiltonian. If you wait for some time, you can do a computation. Just use these techniques of Stanford and Shangar to compute collisions of shockwaves. You wait for some time which is longer than the scrambling time. The firewall gets destroyed by the infalling excitation. Firewalls are fragile things. So if you have a firewall here, you send in an excitation from here, even if it's a very low energy excitation, the horizon jumps out a little bit. So after some time, the firewall falls into the singularity because now it's a little behind the horizon, and so it gets displaced more and more and falls into the singularity after a while. Okay, and therefore, this state psi prime, of course, is as generic as psi by the same argument I made earlier. It's a low energy excitation. And therefore, by these arguments, generic states are smooth, which contradicts what you said in the beginning, which is that generic states have firewalls.
Would they say that the firewall somehow tracks the horizon?
Yeah, I was going to say. New firewall appears also.
So then, so you could do that, but then if you do that, you completely violate effective field theory. Because there's no effective field theory in which you can say that you throw in a low energy excitation, the firewall tracks the horizon. So if you do that, so really, the way to say that actually is that well, there are two ways. That effective field theory just completely breaks down inside the horizon. The firewalls do whatever they like, they track the horizon and they do something, there's no dynamism, there's no, it has to track the horizon immediately, right? It has to jump out.
Can't the firewall, just for purposes of argumentation, track the apparent horizon or something for an old enough black hole?
But I think that this fact that the horizon, that the firewall falls in if you disturb it slightly is rather robust. You don't actually need any global properties of the horizon. The reason the firewall is able to stay where it is without adding any energy is because its distance is such that its kinetic energy is exactly cancelled off with its binding energy with the black hole. You move it a little bit, after some time, it will fall into this energy. I don't know how else.
But I thought your statement that if the firewall jumped out, it would break effective field theory was because maybe I misunderstood, because the horizon is whatever, not a local concept.
Right.
But the apparent horizon or some other thing is a local concept. So could we? I don't know the rules of the game.
Maybe you could do something like this. But this is a computation you can do in effect. Everything I've been doing so far has just been using effective field theory. Sure. So you can use effective field theory to compute the interaction. So these firewalls, you can write down these Stanford-Shanker solutions which behave like firewalls. You can write down some shockwave solution. You can try and perturb it, the shockwave falls into the horizon. That's the basis of the no-head theory. Things fall into the horizon after a while. So it could be. So, but you could, of course, postulate a total breakdown of effective field theory. If you do that, that's basically saying that the CFT doesn't describe the interior of the black holes. And importantly, actually, not only does the CFT not describe the interior of the black hole, the thermofield double state doesn't describe the internal black hole. So if you reject this notion of state dependence, the thermofield double is also not dual to the eternal black hole. So you have, and in fact, that is something that Maroff and Wall did actually propose in 2012. They said the thermofield double is not dual to the eternal black hole, but rather it's dual to the eternal black hole is dual to thermofield double plus some additional subsectors, which actually have to be as big as the original CFT itself. So you have to give up a lot, and that's a little, that kind of throwing out the baby with the bathwater. So this I feel is the most unattractive alternative because it tells you that CFT can't really answer any questions about the black hole material. Okay, but I don't know what the answer is. Maybe this is something that.
Why is the second point
this one?
Yeah.
Well, okay, it's not logical. The statement is that in the eternal black hole also you have these paradoxes which you again resolve using state dependence. So you could say maybe state dependence is. So if you want to reject these notions of state dependence on these grounds, then you have to also reject the eternal black hole or thermofield double duality. Something has to give somewhere. So I outlined a whole set of assumptions, and some of those assumptions has to give. It's not, in principle, you could imagine a setup in which the second is not true, but the first is true. I mean, we can discuss these permutations and combinations. Okay, but I don't have. I wish I had a sharper answer to give you at this point. I don't have a sharper answer, but I think it's an interesting setup. Okay, let me just conclude. I think I'm way beyond time. So let me just say I tried to frame this whole talk in terms of a constructive question of can the CFT be used to describe local operators in a middle of AdS? It's a very natural question. It's a question that should have an answer. I showed you how these questions do have answers in empty AdS and about outside of a black hole, and you can write down these answers explicitly. Then I showed you how if you try to do it now for single-sided black hole, you got these paradoxes. These paradoxes also extend to the eternal black hole. These paradoxes are not only things that are there for pure states in single-sided CFTs, but also for the eternal black holes. And there's a proposed resolution of all of these paradoxes, which is realizing that the infalling observer can only access a subset of the Hilbert space, but not the whole Hilbert space. There's been a more recent objection to this, which is that if you try to do this to describe the interior, then you have this problem that it looks like you can have arbitrarily low energy excitations near the black hole horizon, which are still definitely observable by means of these operators. And as I said, this is an outstanding question. I tried to outline some solutions, but I really think it's an interesting question, and it's a very interesting time to think about this, because it really brings us to the fundamentals of whether AdS CFT works in the presence of black holes and how it does. And either way, whatever the answer is, it's clear that it will be something unexpected. So maybe some of you can also work in that. Okay, good. So I'll stop here.
Questions? ICTS question?
ICTS is gone.
What is ICTS is joining and then we get Suvrat?
ICTS is not there. So, yeah.
Do you have
So you were using this eigenstate summarization hypothesis. So as Nilakash was pointing out, so there is a time-dependent version of saying this, which is which goes under a slightly different name, which is quantum ergodicity and all that.
Okay.
Which is that suppose you take a time-dependent observable and take an expectation value of that in a state, or take an expectation value of an observable in a time-dependent state, and look at it at large times. Now, this observable could be a single local observable, or it could be a string of observables. Now, there is a limitation. Okay, so what is the statement of quantum ergodicity? It's related to the eigenstate summarization hypothesis in some other basis. It is that at long enough times, the expectation value approaches the thermal expectation value, okay, where the temperature is given by the energy of the initial state. Okay. Now there is a limitation to the validity of this one, which is that this string of observables cannot be arbitrary. In particular, what people have been able to prove is that they have to be within a certain compact region. So there's a local region within which all these operators have to be there. So as a result, if you are using some operator construction using the eigenstate summarization hypothesis, I would say that there is a natural limitation of the string of operators that in the sense that there will be naturally a microstate dependence. Okay, on the various results that.
So the precise string of operators as using was modes of single trace operators and products of modes. Such modes which are truncated, so that the total energy is much smaller than n squared. The total number of such modes is smaller than n squared. And I would expect that such operators obey the ETH. In fact, I may even be able to weaken the reliance on ETH and just make the following statement, which is that if you take a typical state pick to the Haar measure, so actually you don't even need the ETH. The ETH is a statement that in typical energy eigenstates, I wrote it somewhere, sorry.
And this ETH is
eigenstate summarization hypothesis, which is a statement that you take and you take an energy eigenstate and energy eigenstate also summarizes. But there is a simpler statement, which is you take the expectation value of an operator. So you take psi, you write down the Haar measure of psi. So you take the set of all states with HE, in the states E plus delta E. This is a linear space in some range. You take an operator X, you average it over this entire vector space using the Haar measure. This average expectation value is the same as the trace over this HE of the same operator X. That's actually small corrections. This is actually a weaker statement than the eigenstate summarization hypothesis. It's not even the statement that an energy eigenstate summarized. It's the statement that the Haar measure average over typical states picked in a microcanonical ensemble are the same as the trace in a microcanonical ensemble, and that is the same as the trace in the canonical ensemble plus 1 over n plus corrections by the usual one. So actually what I needed was this statement. This statement certainly follows from the eigenstate summarization hypothesis, but I think it's a weaker statement.
But you need some kind of... First statement would be true even in the free theory.
This statement?
Yes.
This statement would probably be true even in the free theory probably. I mean, it depends on what operators you're measuring. The free or not depends on what the operator.
But it's really just about the Haar measure.
It's really just
yeah.
Isn't this a notion of genericity of the operator X itself here? I mean, in the sense
that you could probably
need
some operator which violates this. So you could pick some operator which violates this. So it could be that these interior operators are the kind that violate something like this. So one could violate, as I tried to emphasize, that's certainly an assumption. So one could try and relax that assumption and ask for some crazy operators that violate this property. It's possible. Yeah, it's possible that there are some operators that violate this property. So then you see, as I was trying to say, there's a tension in some sense between, the predictions from geometry, predictions from statistical mechanics, and predictions from linearity and unitarity. So you could relax something.
I'm very sorry because we've discussed many things and I'm sorry I only came in at the very end. But in terms of paradoxes of the kind you discussed at the end, is there a sharp paradox which doesn't involve Transplanckian collisions in the end? In the sense that you try to do something with the state at the end, but if you had actually tried to do it as an experiment and prepare that state, you find there would be some Transplanckian collision and you're not really sure about it.
Right. So
sorry.
I tried to say it. Maybe I can answer.
I'm sure you said that.
No, but let me see if I can go back to some of these paradoxes. These paradoxes are so in the end, the question is if you I can here maybe right. So for, the thing is if we believe that effective field theory describes what's happening in the future, then there have to be some degrees of freedom to describe the left and right moving modes. I was trying to say in the beginning, there's some precise conditions you can demand what these guys have to be, what correlators they have to have, these left and right moving modes, which comes just from demanding some conditions for the short distance behavior correlations function, which I can describe. So whatever happens in the future, there are some degrees of freedom which obey the usual short distance correlation relations. That's the statement that the horizon is smooth. You have some degrees of freedom. Using that, you can derive some conditions for the modes, which just follow from Fourier transforming the short distance behavior of the correlators. That already leads you to some paradoxes of this kind, for example. It tells you that you try and evaluate, you have some expectation values for this 2-point function of O with its O dagger, but you also believe that this operator behaves like an annihilation operator, but has positive energy. And if you just use that and some properties of cyclicity of the trace and so on, you end up with some paradox. You find some relation in the role. Now these paradoxes can be resolved using the state dependence construction I showed you. But really, what these paradoxes, the statement is that whatever happens in the past, in the end, are there some simple operators which describe the degrees of freedom, which describe the field, which is a weakly interacting perturbative field in the future. And if so, those operators have to have some properties. Now, the thing about this most recent paradox, these paradoxes I just read some resolution to, is it's possible that this Transplanckian collision. Sorry, I'm going back and forth, but I'm just trying to go back to remind you of some things I said, and now I'll go back. Go here to one of the resolution factors. It's possible that this Transplanckian collision in the past tells you that this commutator between these guys is modified and you don't have this space. But if so, one would ask, what is the correct commutator? That's not easy to do. That just means that I've tried it for a few weeks and not succeeded, but that doesn't mean that it's impossible. So the question is, if possible, that would be a resolution. But then the question is, what is the correct commutator? Write down the commutator that gets rid of this excitation. So you're right, the paradox here is not, it doesn't prove anything because you've left this option open, which is the fact that in these correlators back reaction is important because of this Transplanckian collision in the past. But then either there's some way to make that calculable, or there is a statement that things are not calculable at late times, but if they're not calculable, then you don't believe you get a weakly coupled perturbative field theory at late times. So then the statement is anyway, late times effective field theory breaks down because of these Transplanckian collisions in the past. So yeah. I don't know if that answers the question.
Sorry, one quick question about something right at the beginning of your talk. You talked about the construction of bulk operators in the absence of that. Yes. So just going back to that construction, I wanted to understand what the properties, to what extent those bulk operators obey the properties we expect of bulk fields in a quantity. So for instance, would they commute outside some effective light cone inserted inside arbitrary correlators?
Yes. They're designed to have that property they commute with space acceleration.
But not just in the two-part function.
Yes, in arbitrary.
But they commute inside.
It's slightly cheating. It's cheating a little bit because the thing is that there's a 1 over n expansion, which translates into a perturbative expansion. So at the free field level, they're designed so that all the correlators just break up into products of 2-point functions. So if they commute inside 2-point functions, you're done. Now you could ask, how do you correct it once you add 1 over n corrections? Kabart and Lifshitz have analyzed this in some detail. How you correct this with 1 over n corrections so as to preserve the property of locality. And they have found some answer that shows that you correct this.
That's independent of what other insertions you put.
Correct. So more precisely, they made an analysis for taking a particular 3-point correlation function, adding a certain particular 3-point interaction, or taking some answers for 3-point functions in the boundary, and then asking what are the bulk fields you can write down that would be consistent with locality in the presence of this 3-point interaction. And then that's right. So you certainly want it to be independent of what other insertions you put, as long as you don't put a non-perturbative amount of insertions. As long as you don't put n-squared insertion. If you do that, by the way, you know that locality has to be violated, which is the statement that this quantum error correction people have pointed out. Which is just a statement that if you take all operators on a time slice, it's this time slice axiom, on the boundary at a certain time slice, so that has an empty commuted. So there is no possible operator you can write down. You see, what you want is, here's the boundary of AdS, here's a small strip on the boundary of AdS. You look at all possible operators in this small time strip. There is no operator that commutes with all possible operators in this time strip. So in particular, there is no way in which locality can be exact, because if you wanted locality to be exact, you want an operator in the middle of AdS which is x. So x of O is 0 for all operators you insert here. So there is no such operator. So what about the notion of locality you have? Can only hold within this x psi that I mentioned, within the effective.
I see. And so the construction of this operator is order by order in 1 over n. And depends on the details of it. Correct. I see. But order by order in 1 over n, it is possible, there's some algorithm that makes it possible to construct such.
There's no algorithm, but there are claims that roughly any solution of the crossing relations on the boundary corresponds to an interaction in the bulk, and using that interaction in the bulk, you use perturbation theory to write down these operators. There are claims that it's always possible. There is no algorithm that it's used. But there's a claim that whatever you do, you can.
Thanks. Okay, so thanks a lot.